Sea surface temperatures have been rising since 1980. However, since mid-March of 2023, the global average sea surface temperature has been off the chart, and 2024 is starting out with global average sea surface temperatures that are a full 5 standard deviations above the average for the past 42 years. Our oceans truly are running a fever, and in this video I will highlight the consequences of extreme sea surface temperatures for our changing climate. To get a good picture of what has been happening, take a close look at this chart of global average sea surface temperatures from the University of Maine Climate Reanalyzer. 2023 global sea surface temperatures started out quite warm, but not at record levels. The picture began to change in mid-March of 2023 and became more extreme as the year progressed. Data from the first 2 weeks of 2024 show that the pattern of extreme sea surface temperatures is continuing. We now know that about 91% of the excess heat in the atmosphere that has resulted from greenhouse gas-induced global warming has been absorbed by our oceans, which cover more than 70% of the surface of the Earth. We also know that most of this absorbed heat is contained within the first few hundred meters of the ocean depth. Near-surface heat does eventually mix into the deeper depths of the ocean, but that mixing is very slow. Climate scientists estimate that the total thermal energy contained in the top few hundred meters of the oceans is approximately equal to the total thermal energy contained in the entire atmosphere. Here is a brief list of some of the consequences of rising sea surface temperatures, which I have discussed in more detail in other videos on my YouTube channel. This video focuses on how thermal energy is transferred between the ocean and the atmosphere and vice versa. To understand why the global average sea surface temperature has been increasing since 1980, we need to examine the Earth's energy budget. As shown in this figure, the thermal energy flux that comes into the Earth from solar radiation every day is about 340.4 watts per square meter. On average, 99.9 watts per square meter are reflected back into space by clouds and particulates in the atmosphere. Another 77.1 watts per square meter are absorbed by the atmosphere itself, so only about 163.3 watts per square meter reach the surface of the Earth on average. This solar radiation warms the part of the Earth that is in daylight, and the part of the Earth that is in darkness emits infrared radiation to outer space. Over the course of a day, the outgoing thermal energy flux should exactly balance the incoming flux for the average surface temperature to remain stable from day to day. Infrared radiation leaving the part of the planet that is in darkness would cause temperatures to plummet were it not for greenhouse gases like carbon dioxide, water vapor, and methane. Molecules of these gases have the property that they intercept some of the outgoing infrared radiation, and they re-radiate it in all directions, including back towards the surface of the Earth, keeping temperatures from dropping too low in areas in darkness. This is the atmospheric greenhouse effect. When the amount of greenhouse gases in the atmosphere is stable, the average surface temperature over time would be stable, and on average, the incoming solar energy flux would be exactly balanced by outgoing infrared radiation. But things can change. For example, changes in the emission of particulates from volcanoes can increase or decrease some of the incoming solar radiation reflected by the atmosphere. When this happens, average surface temperatures adjust over time so that the incoming solar flux hitting the Earth's surface again is exactly balanced by the outgoing flux of infrared radiation. Likewise, when the concentration of greenhouse gases in the atmosphere changes, surface temperatures adjust over time to bring the outgoing thermal flux into balance with the incoming flux. However, since the start of the Industrial Revolution, greenhouse gas concentrations in the atmosphere have been increasing on average. This has created a small but steady imbalance between the incoming solar energy flux and the outgoing infrared radiation flux. The amount of the imbalance between the incoming flux and the outgoing flux has been small, only about 0.6 of a watt per square meter since 1980. As I have noted previously, about 91% of this excess heat has been absorbed by the oceans, and this is the primary reason that sea surface temperatures have been rising since the 1980s. Although the energy imbalance between incoming solar radiation and outgoing infrared radiation has been small, only about 0.6 of a watt per square meter, it has been enough to cause sea surface temperatures to increase, and this increase has consequences for our climate because it causes additional warming of the atmosphere. Here is how that happens. We know that the sea surface emits infrared radiation, and that much of this infrared radiation reaches outer space. However, because of the greenhouse gases in the atmosphere, some of the infrared radiation that is emitted by the sea surface is scattered in all directions, and in that process, some energy gets transferred to other gases in the atmosphere. However, a more important mechanism for transfer of thermal energy from the sea surface to the atmosphere is evaporation. You no doubt have observed that if you leave water in a glass at room temperature, over time the water in the glass gradually evaporates. Currently, average sea surface temperatures are running around 21 degrees centigrade, which is right around room temperature. So the oceans are a giant source of evaporation. Physicists refer to the thermal energy that's transferred into the atmosphere by evaporation as latent heat, because the thermal energy that's tied up in the water vapor produced by evaporation doesn't get transferred to the other gases in the atmosphere until the water vapor precipitates as rain or snow. But that happens rather quickly because the mean residence time of a water molecule in the atmosphere is only about 9 days. The water vapor that evaporates from the sea surface is important for two major reasons. The first one is that the water vapor itself is a greenhouse gas. That means that the more water vapor that is evaporated into the air, the warmer the surface of the Earth becomes. The second is that even though the mean residence time of water vapor in the atmosphere is only about 9 days, that's sufficient time for wind to carry water vapor from ocean areas to land areas, contributing to the more extreme weather events we have been experiencing from climate change in recent years. And as the average sea surface temperature increases, more seawater evaporates each day, creating a positive feedback effect that leads to more surface warming. The change in the amount of ocean heat content in the upper 2 kilometers of the ocean is shown in the figure on the left, which is from the National Centers for Environmental Information of the U.S. National Oceanic and Atmospheric Administration. If you look carefully at the chart, you can see that the slope of the ocean heat content curve has been increasing with time, which is an indication that global warming has been accelerating in recent years. It should be apparent from the data that I presented in this video that the recent rapid rise in sea surface temperature is sending us a warning about the state of our climate. Thanks for watching, and if you have any questions or comments, post them in the comments section of the video, and I will do my best to respond. In addition, please take some time to watch my other videos.